Reasoning with exponential graphs. In this video, you'll learn how to explain the meaning of the intersection of the graphs of two functions in terms of the situation it represents. You'll also learn how to write an equation for the function when given 2 points. So exponential functions are in the form f of x equals a times b to the x power, where a represents our initial value, or the y-intercept, and b represents a growth factor if b is greater than 1. But it will represent a decay factor if b is less than 1. We can compare different parts of an exponential graph. The steepness of the graphs will help us compare their growth and decay factors. And the y-intercepts will help us compare the graph starting values. An intersection of the two graphs represent a point where both functions produce the same value. If we have 2 points on the graph, we can determine the equation of the function. We can use the ratio of outputs to inputs to find the value for b. We can find a by plugging b in one of the points into the exponential formula. So let's look at some examples. Here is a graph representing an exponential function f. The function f gives the value of a computer in dollars as a function of time x measured in years since the time of purchase. So when we look at our graph, we can see that the x-axis represents the time and the y-axis represents the value. We want to know what is the purchase price of the computer. Well, this is shown when x is equal to 0, so this is the y-intercept, which gives us a value of 400. So the computer was $400 when we purchased it. Now we want to know what is the meaning of f of 1. So this tells us that x will be 1, and we can see this on the graph where the point is. And this would tell us the value of the computer after 1 year. Now let's write an equation to model this graph. So we'll take our exponential function of y equals a times b to the x power and fill in a and b. A represents our initial value, and we know that was $400. Now let's find b. We'll zoom in so we can see all of the steps. We see that our initial value happened at 0, 400. So we'll rewrite our function and y will become 400 and x will be 0. The next point we see on the graph is 2, 100. So we'll write this function and replace y with 100 and x with 2. Now we're going to divide the second value by the first value to try to find b. 100 divided by 400 will give us 0.25. And a divided by a will just give us 1. B to the second divided by b to the 0 power will get b squared, since dividing exponents just means to subtract the exponents when the base is the same. 1 times b squared is still just b squared. Now we can solve for b by taking the square root of each side. This will give us b is equal to 0.5. Now we can go back to our function and replace b with 0.5. Our next example shows graphs representing two functions and the descriptions of the functions. Function f represents the area of a wall that is covered by mold A doubling every month. And function g represents the area of the wall that is covered by mold B but tripling every month. If we look at our solid curved line, we can see that this one is growing at a faster rate. So this must be function g since this one's tripling, which means our dotted line must be function f. We can see that function f has a higher y-intercept, so this means that it started out with more mold than function g. Now we want to know, what does the point PQ represent? This tells us that after p months, there was the same amount of mold Q for both functions, since that point is on both lines. Our next example gives us a graph of P, an insect population, W weeks after it was first measured, and the population grows exponentially. We want to know what is the weekly factor of growth. So we'll take our function y equals a times b to the x power, and we'll use the points given to replace the x and y in our function to find what a and b must be. So for the point 1, 900, x will become 1 and y will become 900. For the point 3, 8100, y will become 8100 and x will become 3. So now we can divide our second point by our first point to find b. 8100 divided by 900 will give us 9, and a divided by a will give us 1. B cubed divided by b to the first power will give us b squared. B squared times 1 is the same as just b squared. So now we can solve by taking the square root of each side, which would give us a value of b equals 3. So this tells us that the growth factor is increasing by a factor of 3. In our last example, function f is defined by f of x equals 50 times 3 to the x power, and function g is defined by g of x equals a times b to the x power. How does a compare to 50? So in function f, 50 represents the initial value, and in function g, a will represent the initial value. So if we look at both of our y-intercepts, which represents the initial value, then the value of a must be greater than 50 since it's at a higher y-intercept. Now we want to know how does b compare to 3. So now we're talking about the growth patterns. We can see the value of b must be less than 3, but larger than 1 because it's growing slower than function f. Now let's recap what we've learned. If we have enough information about a graph representing an exponential function f, then we can write a corresponding equation. We can also use graphs that compare functions by looking at growth rates and initial values.